Okay, so yeah, it's working. Okay. Yeah, exactly. Yeah, I'm gonna be here to talk about eCash and more specifically, a bit of what we're doing and why we're doing it and what to expect next. I'm gonna repeat some stuff that I said before in like if someone have Pierre has watched previous presentation of mine, there are gonna be some repetition, but I thought it was important because um you say like one piece and another piece over the years in like one presentation and another, and you're several years later, and a lot of people have probably missed some of the pieces, and the whole story doesn't really make sense. So there are gonna be some pieces you've already heard, but overall there are gonna be new stuff as well. So we're doing digital cash, or electronic cash, I guess, because of the conference name. Um, and there are a few characteristics that we want. So Bitcoin is a good start, but there are a few stuff that are not quite where we want them to be for digital cash. And the two ones I'm gonna focus mostly on today are fast confirmations, because well, if it takes on average 10 minutes, like 10 minutes is way longer than what people expect for a confirmation when they pay for something. And scalability, right? Because if a lot of people start using it and it doesn't work anymore and you cannot pay anymore, then it's not a good digital cash experience. Obviously, there are a lot of UX question and all of that, but I'm talking about like what's going on at the infrastructure and protocol level, and those are going to be the important aspect at that level. Okay, so what we want is you want to know if your confirmation is like going through or not within 3 seconds, really, right? And there is a lot of research that have been made about that by, credit card provider or whatever. Ideally, like 2, 3 seconds is like a good time for people to pay. When it's more than 3 seconds, people think it's a bad user experience. And even like it's not written here, but what you notice is like more than 5 seconds, actually people start wondering if it's broken or if it's actually gonna work or not, right? Like 5 seconds is the trigger, like, oh, is my card actually going through or not, right? And so it's where it's where the UX start to get bad. But like, 2 to 3 seconds is the kind of time that people expect it's gonna take for an electronic payment. And so it's really like the target. Obviously the faster is better, right? Like 100 milliseconds, if we could do it, is even better. But like generally people happy with 2, 3 seconds, and but above 3 seconds, I'm not very happy with the experience. So this is what we need to target. And yeah, scalability, obviously, like you want the network to keep chugging along even if a lot of people use. All right. At the core of all those problems is the problem of entropy. So entropy is like a fancy word. People use it to say everything on its reverse, but actually, like, this is actually entropy as it is understood in information theory. We have an entropy problem because the digital cash network that we have is decentralized, right? There is not one authority that say, hey, like this transaction is good, this one is not good, this one was true, this one did not. So as a result, you have several actors that have to make this decision for themselves. And like it's literally impossible. It's not like just a technical limitation, but it's like it's literally impossible for all of them to receive all the same information at the same time in the same order or receive them at all, right? Sometimes there are packets information that get lost along the way. And so the entropy in between all those network participants naturally increase over time, right? So which means the view they have of what the state of the world is gonna drift apart over time, right? So some of them are gonna consider a set of transactions as valid, but maybe like another node did not receive some of those transactions. So no, the state of the world with that other node is like, the same with those few transactions less. And that compounds over time. So we need a consensus algorithm that will, like bring back everybody together toward a common worldview. Otherwise, we have like one version of the system per participant, and it's not very useful. And so yeah, a few examples is like some transaction may have been seen by some node but not seen by others. Um, some node may have accepted some transaction, maybe not other. They are double spend. There are problem of chronological ordering, right? Because they may have seen the same transaction, but they have not necessarily arrived in the same order. So they're gonna disagree on what the set of transactions that have been made on the network is gonna be. And the way we reconcile that traditionally on a Bitcoin style network is by finding blocks. And when you find the blocks, then everybody kind of like by consensus or, by running the protocol, it's the rule of the protocol, agree that whatever is in the block, I'm simplifying a bit here because they can be a competing block and whatnot. But generally, what is in the block is what everybody is going to agree that, is the valid state of the word, even if it's not exactly the state that, they believe the word to be in. That's good, but that's slow, right? Because we find a block every 10 minutes. That means that everybody drifts apart slowly for 10 minutes and then come back together. And so what happens? You have to imagine that, like I have several diagrams, but you have to imagine that operating in like some state space, right? It's not like an actual space. The nodes are not moving physically, in space, but they are moving in, try to imagine like the whole slide of all the different way you can view the situation of the word, like the different transaction that you can include or not, the order of that. This is a virtual space that represents the state of the word. And what happens is like, when a block is found, then all the nodes are roughly at the same place in the state space. They agree on what is the content of the block. But then as time goes on, they're going to start to drift apart, see different things or see the same thing in different orders or a combination of both. And entropy in the system as a whole increases. And so what happened next is that, well, you find another block, and the node that find the block, in that case, it's not one, is very happy because he set the word in the state that it's in. But the other one, they see the word in another state, right? So now they have to run some kind of algorithm to like convert their internal state to be whatever is in block 11 here. And then you're like, the end state is that like everybody agrees on what is in block 11. And it's not a very efficient way to do things, mostly because of that, right? So for the vast majority of the time, you don't do very much and you slowly drift apart, right? And suddenly a block is found and everybody has to work very hard as fast as possible to reconcile all the state and then go back to doing nothing for 10 minutes. And so first, it's like a very efficient use of resources, but second, it's also a scalability factor, right? Because how fast you can propagate and validate blocks is essentially your limit on scalability. That times needs to be negligible compared to the block time. Negligible, obviously, is not a very precise engineering term, and people are gonna disagree on exactly, how much negligible means or not. But essentially, like you intuitively, you see very well that if it takes 10 minutes to propagate and validate the block, then by the time you propagate and validate a block, a new block is found and like the network splinter into an infinite number of forks, right? So if it takes 10 minutes to do that, nothing works at all. Obviously, if it's instantaneous, then no problem, right? And it's not like a binary thing. It's like the longer it takes and the worse the characteristics of the networks are. So ideally, you want to capitalize on that blue space a bit if you want to make things more scalable, right? Because otherwise, like there is only so much you can do in the orange space here to make things better. Right. So pretty much what I just explained, but in text. So what do you want is like, okay, so what do you have ready? Like you have the nodes that drift apart and then, like essentially what I explained. So, but from a user's perspective, it has problem as well, right? Because transactions are in a bit of a quantum state before the block is found. You don't know if it's going to be accepted by the network or not. You don't know if there is a double span really. You don't know very much. You can still do double span proof. I know there is a double span, but you're not that much better now because you still have to wait 10 minutes to know if your transaction or the double span is going through. So, at the end of the day, it's not a great experience. It's bad for the user. It's bad for scalability. So like the natural conclusion is like, if you want to make all the characteristics we care about better, you could find like patches for each one of them and find some kind of solution. But really like the core problem that you're fighting against is the entropy of the system increasing. And the way you want to solve that, if you want to make things consistently better on all the front, is that you must fight entropy continuously, right? So instead of doing nothing for 10 minutes and then working very hard against entropy for a short amount of time and then going back to doing nothing, you would want to, keep entropy low during that whole blue time, right? You're going to be fighting against the entropy continuously. Okay, so you have a few angle of attacks. One of them we tackled a long time ago, but it's still worth mentioning. You remove dimension in which the node can drift apart. And one of them was the transaction ordering, right? If you get rid of that, like before the node, they could disagree on which order the transaction arrive in and which order they should be in the block. But if you say, hey, there is like an objective canonical order that is given by the protocol, then the only question is like whether each transaction is included or not. It's not in that order. And so you have a whole dimension or, class of problems in which the node could drift apart that just don't exist anymore by definition. And it's more significant than you would expect intuitively, right? Because whether a transaction is included or not in the block is one bit of information, right? Really, it's included or it's not included, right? So it's just one bit of information. But if you think about it, there is a lot of different ordering you can have, even for like a small number of elements, right? And there is actually n factorial ordering, because the first, if you have like 10 elements, the first element could be like one of the 10, right? And the second element is like one of the 9 remaining. So the one that you already put is removed. And, so it's like 10 times 9 times 8 times 7. And like, it's a really, really big number already. And it's just like 10 elements. So any reasonably sized block is going to have like a huge number, like an absurdly huge number of ordering possible. And if you run the number, with information theory, you realize that you need n log n bits of information. So you actually need way more. You need way more information to convey in what order the transactions are than you need to convey if the transactions are included or not. And like to give an idea, like it's actually quite a bit, because if you have like 1,000 transactions, you have about a 10x difference. So you need like 10 bits of ordering information for 1 bit of inclusion. And if you have a 1 million transaction, it's 20x. So, at some point, it tapers off, but it's still, like a huge amount of information. So just by doing that, you remove, 90% of the problem. Like 90% of the state space the different node can drift into is just gone. So that's a huge improvement. And so we did that like a long time ago, but was worth mentioning. So the second thing that you want to do after that is Avalanche, or at least that's one way you can do it, and that's the way we choose for eCash. So what you do with Avalanche is that you have the node continuously talking with each other in between blocks to, decide for, each blocks and each transaction and each whatever, wonder what the other node are thinking about it. And maybe, if you see that yourself, you're in the minority, like most node, they choose to go in a different direction, you are going to flip your own position. So for instance, there is a double spend going on. You consider that one of the transactions is the right one because this is the first one you receive, but you're going to ask the other nodes, hey, have you seen this other transaction before? And if they all tell you yes, you're going to be like, okay, maybe, maybe I am actually the one who was wrong here. So I'm simplifying quite a bit. There is a way to do that is rigorous and that you can prove is going to converge toward a decision and that is resistant against, some actor fucking around by sending random messages. But like the general idea is that, right? Like you ask other nodes, if you're a node, you ask the other node in the network what they think of the situation. And if most of them think differently than you do, you're going to switch your position. And what happens when you do that is that as time goes on, the nodes, they, keep building in the same direction. And so when the block is found, then they're roughly all at the same place and don't have much work to do because they did already most of the work over time while the block was being mined. And so an example of that is something we use to protect about some kind of 51% attacks. So what happened? Like, okay, you have blocks that are being mined and being found is like very, very typical blockchain, schematics. Okay, so let's say an attacker has more hash rate than whatever is mining on the chain, and is mining a secret chain. Like we don't see it, but at some point that attacker is gonna release like all the chain at once. and all the nodes are gonna reorg into like this guy, right? When you see that block 4 prime coming and the whole chain that goes with it as a node, like, how do you know whether you were the one that was mistaken, like this block was there all along, but for some reason, like you were not notified, or whether it's actually an attack, someone that is, has been mining on its own on the side, not publishing the block and running a 51% attack. And it's actually not a decision you can make by yourself on your own, right? Because you cannot be sure that there was not, the block out there known publicly, but for some reason it was not sent to you because maybe like the packet was dropped, you lost the connection to the other node that was sending you the block, or like whatever happened, for some reason you did not receive it. You cannot prove that, this block was not there. But with something like Avalanche, you can continuously talk with the other node and be like, I received the new block and there is the new tip of my chain. What do you think about it? Right? And so at the beginning, you receive a block, and based on your subjective, assessment of the situation, you're going to connect the block or not to your chain, but then you're going to ask other node. And within 2 seconds, you're going to see like whether other node are like, well, this is also my tip, or no, I'm on block 3 and I've been there for like quite some time. So your block is like probably an attack. This way, you can make sure that it's not just you that have not seen that block before, but it's you and everybody else, or at least the majority of the network that have not seen this block before. So now you can make the difference between, oh, there is a race condition, 2 people found the block roughly at the same time, and well, this is a natural stuff that happened on the network. It's part of the consensus algorithm, or someone did something malicious. And you know that someone did something malicious because everybody was able to agree on block 3 at some point. So now when you receive the block 4 prime, you're like, well, this is a reorg of a block that everybody agrees is the tip, and this is clearly someone that is screwing around with the network, and you can reject that block, even if it has, more work in there. So that's a way to prevent like some class of 51% attack that we have actually experienced in the wild. So this is like not a theoretical attack and whatnot. This is what people actually try to do, and we know that it works. We know that it works the best way we can. Okay. So yeah, you have this block 4 prime. Is it an attack? Well, you don't know by yourself, but some reorg naturally happen. But you can discuss with other nodes and see, like what they think of the situation. And if your is like, well, we saw the other one before, then it's an attack. All right. So I explained roughly, same stuff. They not deploy each other, blah, blah, blah. Another thing that we can do is heartbeat. So this is something we deployed. I don't think it was mentioned in the talk so far, but this is something we deployed last year, roughly, like a bit less than a year, but almost a year now. So something that we see on the network is like sometimes a lot of miners, are coming on the network, mining a lot of block on a very short amount of time, and then the difficulty goes up, and then you have no block for a while, and then, so on and so forth, and the cycles repeat. And it's not a very good user experience for, the users, right? Because sometimes you get like very fast confirmation, and sometimes you have to wait for a fair amount of time. So what we can do is make decision whether we accept a block or not based on something that is subjective. And in that case, it's going to be the clock, right? Or the clock of the computer on which the node is running. And the thing is, like, each clock is not perfectly synchronized, and there's no possible way to achieve that anyway. And to begin with, it takes time to propagate the block on the network, right? So even if each clock was perfectly synchronized, the nodes, they don't receive the block at the same time, so it wouldn't fix the problem anyway. But you can make a subjective assessment, like based on when I received that block and based on my clock and when I received the previous block, like is it something that served the network or not, or something I should reject? And you can make that subjective assessment. Now, the block is not invalid, right? So you cannot mark it as invalid, but you're going to mark it as what we call parked. So I'm not going to connect it to my blockchain. I'm just going to put it on the side. I know it. I know it's there. I know it's technically valid, but I'm not interested in that block. But then I want to remain in consensus with the rest of the network, right? So I can run Avalanche with the other node on the network. And maybe, if they saw the same thing as me, they would have made the same decision and everybody's going to reject the block. But maybe, for some reason, like before, the block took a long time to arrive to me, or my clock settings on my computer is not set properly or whatever. And that led me to conclude that, I should reject that block when I should accept it because everybody else accepted it. So the fact that we have that mechanism allow us to make those subjective decisions and then have everybody, like all the nodes talk with each other through Avalanche to reconciliate, those subjective decisions where they end up being, the same or not. And if they're not the same, you're like, well, I thought that it was a bad block, but I'm going to accept it anyway. And that has increased quite a bit, the quality of the user experience by making block much more regular than before. Obviously, they're not perfectly regular because mining remains a probabilistic process in nature. You cannot make them like every 10 minutes, tack. But it's much better than before where we had, switch miner that would mine block very quickly and then space them out quite a bit. All right, so I gave 2 examples, the post-consensus and heartbeat. But obviously, one thing we've discussed a lot, throughout the year is preconsensus. And preconsensus is essentially the same idea, but instead of doing it with block, you do it with transactions. Right, so to fix the first one, I know I'm talking about block here and it's purposeful. To do the stuff that we did before, we decide which block is seen first or which block we want to accept or not. And then we run, the algorithm network-wide to, so that everybody agree, right? And you can do the same thing with transaction, right? Like it's the exact same sentences. You can establish which transaction are seen first network-wide in the same way you do it with block. And you can use that knowledge to mitigate not 51% attack, but double spend attacks, right? It's the exact same idea in principle. No, it's very simple in principle. It's not so simple in practice. It's why, it's why we're at it for quite some time. And there are a number of reasons for that, but the main reason is like, first, you're guaranteed to not get so many blocks at the same time because producing a block is a complicated process. There is proof of work. When it comes to transaction, people can just flood the network with a bunch of transactions. It's very easy to produce, conflicting transaction, whereas it's going to be costly to do that with blocks. I mean, like costly, like quite literally, you have to expend computing power and electricity to produce those blocks. So, on that front, like the attacker has much more option to screw with the system and to a much higher degree and much higher volume. But also, you have all kind of problem like the block template construction. So miners, they connect to a node so that the node can tell them, hey, here is what I think the next block should look like, and then send that to the mining rigs. So there are ramifications in all of that in like, you construct the next block and so on. So it's quite a bit more complicated to do in practice, even though the principle is the same and it works for the same reason. There are just like a lot of implementation details to nail that are much more complicated than for blocks. But what you get from the user perspective is that, well, a user can know if the transaction is final or not in about 2 seconds. And the block content is more predictable, right? And if you know what the next block is going to be, the amount of work that you need to do, and it goes back to scalability, the amount of work that you need to do is lower, which also means that you can produce bigger blocks. And overall, that means that you don't get bottleneck for users when the network is full and, they get like very fast feedback. They can send a transaction and within seconds they know, hey, the transaction is final, good, can move on with your life. That it may not be in the next block, but it's going to be in the block eventually. And no double spend is going to be, it's going to be mined, right? So the reason you don't know necessarily if it's in the next block is like maybe someone is already mining the next block, and didn't have time to include your transaction. But in general, also what when you know that your transaction is finalized, that the node you're connected to has run Avalanche and has considered the transaction finalized. But what that guarantees you is not necessarily that everybody has reached that conclusion yet. What it guarantees you is that everybody running the protocol honestly will eventually reach the same conclusion as you do, right? Because there is no synchronized clock for everybody on the network, right? So the other participants, they're going to run, but they may be a bit later than you are, and they may come to the conclusion, like a second or two later or whatever. And for that reason, you cannot really guarantee that the transaction is included in the next block, but you can guarantee that no double spend is included, and then it's a matter of time before it finds its way into a block. Okay, another stuff that we can do is just the same as heartbeat. You can start making decisions based on subjective criteria, right? And you can be like, well, I have a lot of transactions in my mempool. I think there is some kind of spam attack going on, so I'm gonna raise the fee a little bit to protect the network against spam, like momentarily, because there is a lot of transaction right now. But the rest of the time, I can keep transaction low. This is an example, right? But I found that it was very funny to think about that right now, because if you've been following what's going on in the BTC world, there are essentially two factions in BTC right now that are fighting pretty hard. A lot of debate and pretty heated one, I would say. Those are the core and the not people, and they essentially disagree about technicality we don't need to get into, but those are policies changes. It's how big do you want the up return to be, or this kind of stuff. And all of those are policies, right? So you can have, it's not a consensus change, right? So you can have one node that have a certain rule for those policy, and another node that have different rules for the policies. If you have a system like that, that debate doesn't need to happen, right? Because you can deploy your node with a certain set of policies, and then your node can make a decision on a transaction, be like, okay, this transaction is good or it's non-standard and I'm going to accept it. And then you talk with the other nodes through the Avalanche protocol. And if all the other nodes tell you, well, we consider that transaction to be valid, you can be like, all right, I don't think it's a good one, but everybody else disagrees, so I'm going to accept it anyway, or vice versa, right? And you could settle that debate right away, right? Because core and node people could start their node and put their money where their mouth is by, providing a proof that they own some amount of coins. And whoever owns the most essentially would impose its policy on the network. And if for some reason, some people get convinced that the other policy is better and they decide to change, well, no, the new policy enters into action. And there is no need for a fork or for a holy war and whatnot. This debate would be essentially solved at the protocol level with this type of system. So I don't know that we really need to do the node versus core holy war, but I think stuff like dynamic fee when there is a lot of load on the network or stuff like that could be useful. All right, so to wrap up a bit, fighting entropy improve on many fronts. Transaction finality, we can do less than 2-second transaction finality. We get better scaling out of it. We get better security against 51% attack. We get improvement in network stability in the case of heartbeat. And we can do dynamic and subjective decision, for instance, on network policy. So for instance, on the fees or on the core versus node kind of stuff, right? This is all we get with essentially fighting entropy, which we do with Avalanche, but really any technology that would allow us to fight entropy would, improve on all those things, because those are all symptoms of the deeper cause that we let entropy grow between blocks. All right, so first we're gonna ask if there are a few questions. I don't know. I guess most people were mostly familiar with most of those stuff, but haha. You wanna know because I have one more thing. We're actually launching Preconsensus. And well, you have it there. There is an upgrade on November 15th, like there is every year essentially. And in that upgrade, we have we have Preconsensus. essentially. So there's still like stuff that we can improve and stuff like that, but it's in good shape and it works. So yeah, it's like it's been a long time, but it's finally there. And I don't know, like I have the same stuff, but I guess we go back to question. I don't know what we're doing in time because there's no clock here. Oh yeah. Yeah, I was not sure. I don't want it to be too long because when you have no clock, you don't know if you're just rambling ever forever.
A lot of the network things that you were describing with blocks and how all the work happens when the blocks come and how it would be nice to do more work in between and how you can improve the user experience, everything. It seems like all of that would also apply to BTC. Can you
Yeah.
comment on why BTC has never attempted to do something like this? Even though, there used to be a narrative on BTC that, if other projects do something and it works, we can just copy them.
I have something that may surprise you, but I think Greg Maxwell actually came up with the word preconsensus. I'm not sure. Yeah, I think so. At least this is what I remember. So this is something that was discussed in the Bitcoin cycle in the early days, but I don't know. It doesn't seem to be of interest to people right now. And I would say, if you limit stuff to 1 megabyte and you reach that limit on a regular basis, like this is not gonna help, right? Because you don't have the capacity to send the transactions through anyway, and you start to have really perverse incentive when you have that, right? Because are people gonna follow the pre-consensus or are people gonna follow the fees? If the fee gets really high, you have an incentive for some actor to not do the pre-consensus, and that's the situation gets really, really messy because the incentives are not aligned. So I don't really know. Also, in crypto, you have a bit of an uninvented here, kind of thing that happened. To be honest, like we had another idea for a protocol before Avalanche, because we started working on that like before Avalanche actually existed. And when the Avalanche white paper came about, we're like, well, this is doing essentially this is a simpler and better version of what we were doing. We were doing like something based on the same idea, but it was more complicated and it was somehow less efficient, even though it was more complicated. So there was no reason to keep it, and we adopted the Avalanche solution. But yeah, in my experience, for some reason, many teams are just not willing to do that. But like not only you could do it on BTC, but you could do it on Litecoin and on Dogecoin and on like with a bit more work. But you could probably also do it on chain that are a bit more different, like Monero and whatnot. Like you could probably do it on every single UTXO based chain to some extent with more or less work.
Yeah. Oh, thanks. It's interesting.
Okay, we got a question in the chat here, Amaury.
Yep.
Question: What about future upgrades? Now that Preconsensus is done, what's next?
Already. What I would say, just like when we released post-consensus, we could do some nice stuff with it that we didn't do right away because there is value, to put it out there before everything is perfect. We could do our bit later on, for instance. I think there is a fair amount of stuff that we can do to make pre-consensus better, or to use it to do stuff. So I think like the dynamic fee stuff is probably something that we want to do because we can drop the fee to essentially zero in like normal network operation while remaining protected against, kind of attacks because we can do it dynamically. You can also probably like get rid of the block size if you just like increase the fee as the block gets bigger or something like that. I haven't, like run experiment with those stuff, but those are like ideas that people probably want to think about. There is a lot of stuff that you can do with that we're not really gonna do right now. Like the first version is just gonna finalize transaction or not. There are also limitations in terms of throughput in the first version. So if there are a lot of transactions, some of them, they may have to wait a round of two. What a run is going to be like about 2 seconds, right? It's not like it's going to take forever, but if there are, a lot of transactions, it's going to take a bit longer, even though this is not a technical limitation. This is a limitation of the current implementation. We could do all of them in 2 seconds, really, like technically. Uh, there are ways we can improve what we're gonna release on November 15th, but I think, it's always preferable to just, release something that add values, and plus you get real world feedback, right? So based on the real world feedback, we're probably gonna also have ideas on what to do next. But I would say, yeah, leveraging what we're gonna release in November, to deploy stuff is probably the next step. It's what's gonna get the most bang for the buck.
Oh, maybe I'll ask one more question from the chat. It's about, I think it's about staking rewards. It says any change in the node reward selection for pre-consensus, whether using voting or still using existing mechanism.
Yeah, so there are a couple of other changes that are in the upgrade that I decided to not talk too much about during the presentation because they are a bit more technical. And if you talked about like 5 different stuff, then you talked about none of them really. So I wanted to focus on the important one. But I think there are 2 notable changes that we need to mention. One is on the staking reward. We're gonna use Avalanche to essentially like pre-confirm who is gonna get the next staking reward before the block is actually found, which because I increase the reliability of that's chosen, and like, yeah, the overall staking stuff is gonna be more reliable because of that. And the second stuff is the script, the 64-bit integer. So I think someone mentioned it this morning that it was Yeah. So we're gonna have a 64-bit integer in script in that upgrade as well.
Can you hear me? Yeah. So it's pretty funny that like we added 64-bit integers, but like the only guy who talks about it was like from Bitcoin Cash. That kind of shows the cultural orientation, I guess. But yeah, we just had to fix it. So one question is regarding Avalanche subnets. Like these have been around for like a really long time. And I think I like from what I understand, I think it's a really, really good idea. So generally, what are because you did mention them, what are your ideas today on this? And on something very specific, I recently had the idea that you can actually use Avalanche to to inspect other blockchains. So like, did this transaction happen on like Ethereum or something? Yeah, what are your thoughts on that, basically?
Yeah, so like you mentioned why it is the same reason Swift Network is the same reason that you mentioned that you can look other blockchain. Avalanche essentially solved the reverse spec problem. So for the longest time in Bitcoin, there was this idea of like subchain or sidechain, or they have like different drive chain. They all have different name and they have mechanisms that are a bit different on how they work exactly, but they all have something that they don't do very well is the reverse. Like, so you can send your money on the sidechain and it works very well, but when you want to bring your money back on the main chain, it's always a complicated process, and we had no good solution with that because you need to run 2 consensus between like 2 different networks that are not necessarily happy to be in consensus with each other. And if each of them converges slowly, like once every 10 minutes, once you have the 2 of them that need to be converging together, it can take like days or even weeks or months for some of those systems. Which is not great. But with Avalanche, just because Avalanche is much faster, you can do the same kind of thing, except you can do them very quick. And this is why Subnet works. Subnet or sidechain and stuff like that. You can move your coin to some other system that have like whatever rule you want them to have. And then you can bring them back, and you just need to agree on the protocol to do that. And you can have those not watching other blockchain as well. The reason it's, I think, valuable, like there are two axes, but one of them is you can allow innovation that way. That would be complicated, right? That will require hard fork or stuff like that. But you can be like, okay, I'm gonna do like this other network that have a different rules, and if I can move money back and forth, then it's fine. Actually, like if Bitcoin had that, for instance, well, there would be no block size debate, for instance, because you could do like your big block version of Bitcoin on a sidechain, and everyone who want to use that, right? So I think in terms of like innovation and evolution, it's very, very interesting. Um, and the second aspect, I'm losing it. I had to.
Before that changes, for example, like cost in the blockchain communication.
Yeah, but so that's because you can do like any rules in there, right? So it can be an EVM, it can be like a zero knowledge stuff, but actually this is where I wanted to go. Something that I think is very, very important is privacy, and Bitcoin style system are very poor privacy. Um, but when you bake privacy into the system, you have like all kind of problem that comes out of that. So if you look at Monero, for instance, which is one of the most famous privacy chain, you have essentially two problems with Monero. One is the UTXO set is growing forever because you don't know what is spent or what is not spent, right? So it's not a UTXO set, it's like a TXO set. All the transactions are unspent ever, or you cannot know if they've been spent. And so you have like huge scalability issue on that front. Another problem is that you don't know how much money there is in circulation, right? So if there is a bug somewhere in Monero and someone find a way to print money out of that, nobody's gonna know about it, right? And another example is like Zcash, for instance. Like recently, it was discussed that they had to rewrite their zero knowledge system 3 times, and like to some extent the subsequent version were better than the previous one, but now you have a consensus layer that have to understand like the 3 different systems, and a lot of complication there. Whereas you can do a privacy subnet. You don't know the details of like everything that is going on in that subnet, but you know overall how much money have been moved on that subnet, and you know that you're never going to be able to get out more than what was put in. So in that sense, you still get auditability in the sense that you know how much coins there is in the system. Obviously, you don't know what's going on in the subnet, but if there is something that goes wrong there with the cryptography or whatever, you may not know about it, but you also like the other users that are not involved with the subnet are not going to be impacted. Which is pretty good. There are also legal ramification. We've seen developers, like for Tornado Cash, for instance, that have been in legal trouble, not because they really, at least according to me, they didn't really do anything bad, but some people have used their tool to do something bad, and now the authority are going after them. So if you can do that on the side, it's also like a regulatory protection for the developers, because you don't, if you're not in a position where you are going to be able to defend yourself, you don't have to touch the subnet. So, for all those reasons, I think it's pretty good stuff. And yeah, it's amongst the future stuff. I think like it depends on what time scale we're looking at. A short term, capitalizing on the pre-consensus, but mid-term, putting more on the subnet, I think is, I think it's where it's at.
Absolutely. I mean, EVM-based subnet and also JavaScript-based subnet.
Well, but here's the point. You don't need to ask me, right? Like, that's what is good about it. Like, anyone can start one of those.
That scenario no permit permissionless subnets. Every Avalanche node should have the rules of the subnet.
No, so that's the point, right? Like only the people that care about the subnet can run the subnet, and everybody else, they just have to monitor the input and the output that go in the subnet. They don't need to validate the subnet itself. Yeah, exactly. Yeah, that's the point. It can be an account system, doesn't even need to be a UTXO system, or it can be a zero knowledge. It can be anything. That's kind of the promise of sidechains, but better. And what it really the main difference is the reverse peg. It's really like the problem that made like all the sidechain project and all of that very tricky. Like for instance, you look at, I would say the most promising sidechain project on Bitcoin is Drive Chain, I would say. And to get the money from a Drive Chain back to the main chain, it can take up to 2 months. right? So that's a very long time. And you could say, well, maybe that's not a problem because if we have liquidity provider, you're right, but still, right? It's not ideal, and you could do that in minutes instead. And I think this is where it makes a huge difference in terms of usability, and I think it unlocks a lot of what you can do with those things. Even though technically you can do the same thing, but practically it's much better to use if you don't have to wait 2 months.
Awesome. Thanks, Amaury.